Okay, this video is on average rate of change. Now, if we have a function, y is a function of x, then this symbol here means a change in y. This little triangle here is a Greek symbol delta, and delta y just means a change in y. Delta x means a change in x. So this average rate of change, and specifically the average rate of change over an interval, that just means the change in y over the change in x over some interval. Now, you're probably most familiar with this in terms of the slope of a line. You're familiar with taking 2 points on a line and calculating the slope between those 2 points. This is very similar, except we're going to also be calculating rate of change for some curves that are not lines. All right, so it doesn't make sense to talk about slope in terms of a nonlinear function. So we're going to be talking about it in terms of rate of change. Now, another thing to note about our definition here of rate of change, typically you see this rate of change defined in terms of y and x. Y equals a function of x. Well, notice that this value here in the denominator, the delta y, the y is just the dependent variable, and the x is just the independent variable. And sometimes those variables might be something different from y or x. It might be, for example, we're going to see in just a minute, it might be t for time, d for distance. Whatever the variables happen to be, you would calculate your rate of change in terms of those variables. So let's take a look at some examples here. Example number 1 says, for graph A, calculate the average rate of change over the interval t equals 2 to t equals 5. And you have graph A here in your notes. So I want to calculate the rate of change over this interval, t equals 2 to t equals 5. So first, let me find out what I'm given my t values here, so I can calculate the change in t, the delta t value. What is my d value? I can see that my two variables here, my independent variable is t, my dependent variable is going to be d. Well, when t equals 2, that's this point right here, I can see from my graph that d is equal to 6. So when t equals 2, d equals 6. And when t equals 5, 2, 3, 4, 5, that's this point about right here, I can see when t is equal to 5, d is equal to 12. So when t equals 5, d equals 12. Now I can calculate my delta t and delta d values, and I can calculate my rate of change. So delta t is just the change from the first t value to the second t value. So it's just this difference here. So delta t is going to be 5 minus 2. Let's do it like this. Let's say t2 minus t1. And that's going to be 5 minus 2, which is 3. Delta d is going to be my second d value minus my first d value, which is 12 minus 6, which is 6. Now I can calculate my rate of change, which is going to be the change in my dependent variable over the change in my independent variable. So delta d over delta t. Well, delta d is 6. Delta t is 3. So my rate of change is 2. Now part B says, calculate the average rate of change over another interval. So let's pick an interval, let's say t equals 3 to t equals, let's say t equals 3 to t equals 7. So what are my d values for t equals 3 and t equals 7? Well, I look on my graph here, and for t equals 3, I see my distance value is 8. And for t equals 7, I see my distance value is 16. So now I can calculate delta t is, so the change in t from t equals 3 to t equals 7, that change is just going to be 4, positive 4. My delta d value from this time t equals 3 to t equals 7, my delta d value is 8 to 16, so that's going to be 8. I take these and put them together, and I can calculate delta d over delta t, which is, my delta d value is 8, my delta t value is 4, and so my delta d over delta t value, or my rate of change, is 2. And one thing I notice is that the average rate of change is the same over different intervals. And that's a particular feature of linear functions. The average rate of change is always the same. That's just kind of another way of saying the slope of a line is always the same, no matter what 2 points you happen to pick on that line to calculate the slope. The average rate of change for a linear function is similar to the slope. Well, let's take a look at this for a non-linear function. So example number 2. For graph C, calculate the average rate of change over the interval t equals 0 to t equals 2. Okay, now here I have a different graph, and I can see it's not linear, but I'm still going to be doing the same thing to calculate the average rate of change. I want to know what is my dependent variable value for these two values of the independent variable. So at t equals 0, which is right here, and I can see on my graph, at t equals 0, d is equal to 2. And at t equals 2, d is equal to 14. So now I can calculate delta t and delta d. Delta t, the change in t over this interval from 0 to 2, that change is a positive 2. The change in d over this interval, d goes from 2 to 14, so that's a change of 12. I take these and put them together, delta d over delta t. My delta d value is 12. My delta t value is 2. So my rate of change, my average rate of change over this interval is 6. All right, let's calculate the average rate of change over a different interval, t equals 2 to t equals 4. So for t equals 2, my value of d is 14. For t equals 4, my value of d is, let's see, t equals 4, my value of d is 18. Read that off the graph. Now I can calculate delta t and delta d. My delta t goes from t equals 2 to t equals 4, so that's a change of 2, positive 2. My d value goes from 14 to 18, so that's a change of positive 4. I put these together, delta d over delta t. Delta d is 4, delta t is 2. So my average rate of change over this interval is 2. And I notice that's different from this interval here, which kind of makes sense because that rate of change looks different on the graph. Let's do one more. What's the average rate of change of this function from t equals 6 to t equals 8? So t equals 6 is right here, and I read off my graph for t equals 6, d equals 14. And for t equals 8, which is down here, t equals 8, d equals 2. All right, so let's see. I want to calculate delta t and delta d. So my delta t value, going from 6 to 8, my delta t value is positive 2. The change in T, going from 6 to 8, is a change of 2. My change in D, going from 14 to 2, now notice that I'm starting at 14 and I'm going to 2, so my change in D is actually going to be a negative value. That is 2 minus 14. My delta D value is going to be negative 12. Well, now once again I'm going to take these two values and put them together in order to calculate delta D over delta T, my average rate of change. Delta D is negative 12. Delta T is positive 2. And my average rate of change now is a negative 6. And again, if you think about these average rates of change as kind of the slope of a line that you could draw between those 2 points, then you can see that the average rate of change here over my first interval, that average rate of change was 6. I can see that the slope between these 2 points is a positive value. The slope between my next 2 points, it's also a positive value, but it's not as steep. So it's positive, but it's not as high as 6. And the slope between my last 2 points is actually negative. I can see the graph of my function is going down. So that's one of the things, let me write that over here. One of the things that is true about nonlinear functions is that the average rate of change is different over different intervals. All right, let's take a look at this example number 3. It says the table below gives the annual sales of CDs and vinyl records between 1982 and 1994. What was the average rate of change? What was the average rate of change of annual sales of CDs and LPs between 1982 and 1984? So I can see from my table here, and this, by the way, is called, it's kind of a combined table. I can see that I've got essentially two different sets of data in a single table. For 1982, I've got CD sales in this row here, and I've got LP sales in this row here. So if I want to calculate, I'm going to calculate 2 different rates of change, one for CDs and one for LPs. So for the CDs from 1982 to 1984, I would like to calculate delta C over delta T. So in order to do that, I'm going to need to know what were the values for CD sales in 1982 and 1984. So my C value for 1982 is 0. My C value for 1984 is 5.8. These are 5.8 millions of CDs sold. Well, now I can calculate my delta T and delta C values. My delta T going from 1982 to 1984 is plus 2. My delta C going from 0 to 5.8 is 5.8. And now I can calculate my delta C over delta T. Remember, rate of change is the change in the dependent variable over the change in the independent variable. So delta C over delta T is going to be 5.8 over 2, which is 2.9. And this would be 2.9 millions of CDs per year. So the rate of change in CD sales, I can see that CD sales are going up by 2.9 million CDs per year over this interval, 1982 to 1984. Well, let's take a look at LPs. Again, I want to calculate, let's see, this is LPs from 1982 to 1984. Let's write this down here. 1982 to 1984. And I want to know now what's the value of my dependent variable for these two, over this interval, for these two values of time. So I look at my table. In 1982, LP sales were 244 million units. In 1984, LP sales were 205 million units. So now I can calculate delta T and delta L, the change in time and the change in my LP sales. So delta T again is going to be 2, the interval 1982 to 1984. My delta L value is the change in LP sales from 244 to 205. Well, I can see this number is going to be negative because the number of LPs that were sold in these years, the number of LPs sold is going down. So this is going to be, delta L is going to be 205 minus 244, which is going to be, what is that, 39? 239. No, 39. So I take these two numbers and I calculate delta L over delta T, my rate of change of LP sales. So my delta L is going to be 39 and my delta T is going to be 2. And 39 divided by 2 is 19.5. 19.5 millions of LPs per year, and this one is going to be, oops, I forgot my negative sign. This is going to be negative 39 over 2, so that's going to be a negative 19.5 is my average rate of change of LPs from 1982 to 1984. Now, I'm going to let you finish the rest of example number 3 on your own, and we'll take a look at this one tomorrow in class.